Okay, so I wrote on the board two results from yesterday that we'll be using today, just to remind you. The first one is the wave function, but now I write down the Bunch-Davies vacuum wave function for zeta. Now I write for zeta. And in the exponent, there's a real and imaginary part. The imaginary part, as I told you on Monday, it tells you that there's some sense in which this state, the fluctuations, they are classical. There's some sense. But today we are not actually going to need exactly what that is. So I just keep it back there just to say it's large. We'll need the real part though. The real part is 1 over the power spectrum with the factor of 2. So that's the first point. The second point from yesterday, I don't know whether you remember, when we look at the metric fluctuations, if you write down Einstein's equations, there are several. There are equations that have to do with delta G ij, the spatial components. And then there are equations that have to do with time, delta G00, and time space, delta G0I components. I was not explicit about what those equations are, but there's one equation we will need. If you look at the 0, 0, and 0I equation of motion, it turns out you can deduce that the following is true, which is what I wrote down there. We are going to need that today. Okay, these are the two things we will need today. Any questions before I start? So today I'm going to tell you something soft. It's going to be a soft lesson instead of a hard lesson. You will see what I mean. Okay, so let me remind you where we were yesterday. No, yesterday we had this observation. That if you look at the spatial part of the metric, I'm just writing the spatial part. And ignore the tensor modes for now. I'll say something about that later in an hour maybe. Let's just focus on this. And recall we make this the following observation. No? If we make this change, this e to the, let me switch the sign from yesterday, but it's really the same. If I make this and do this, manifestly, this spatial part of the metric remains unchanged. Yeah.
Sorry, one more thing about the remark from yesterday.
Yeah.
One over K to
1 over K to 3.
3.
Yeah, thank you. I forget about that part. In my head, I just multiply by K cubed. Yes, you're right. Thank you. That's very important. Thanks. And remember, you are supposed to, it's kind of a tricky expression. Just want to reiterate. You are taking the late time limit of the power spectrum. So once you take the late time limit, the zeta mode is frozen. So this is actually a constant. That doesn't depend on time. But when you see something like this, you are supposed to evaluate this at Hubble radius crossing. You see what I mean? So tell me the K that you're interested in. You ask yourself, when does it cross Hubble radius? Evaluate at that time. But once you evaluate, that's it. That's the constant. And then you can let the mode get stretched outside the horizon or the Hubble radius. Zeta is frozen. It will be the same value. Okay? So it's a little bit of a tricky expression. Okay, so yesterday we ended with this observation. Now, this is manifestly correct. Yeah. What I want to do is to show you the fact that zeta shifts by this amount. The fact that it shifts by an amount that is independent of zeta, that's what we call a non-linearly realized symmetry. And it turns out there are soft theorems associated with that. So that's basically the main topic today. Okay. And to do this, I'm going to be a little bit more precise when I say this. So here's what I'm going to do. So I'm going to say we are going to transform x to x prime, where x prime is defined to be precisely this. And we are going to consider a small lambda. So think of lambda as a small parameter. It's the transformation parameter. So lambda, we are going to think of it as a small transformation parameter. And so this is roughly equal to 1 minus lambda x. Okay, this is my x prime. Yeah. And then the point is zeta now get replaced into zeta prime equal zeta plus lambda. That's what we mean. But here you have to be a little bit careful because zeta itself is a function of space. And so you have to ask yourself, when I say zeta prime as a function of x or x prime. And the right way to say is this is really a function of x prime, and this is a function of x. This is the right relation. You got that? In other words, I'm saying something actually is not too profound. All I'm saying is that a squared e to the 2 zeta prime as a function of x prime dx prime square is the same as e to the zeta as a function of x dx square. You got that? That's all I'm saying. This is the same as that. It's just a more elaborate way of saying what you already recognized yesterday, that this leaves this line element unchanged. Okay? But now we are going to use this, and in particular, I'm going to expand this now. So this is at x prime, and this is at x. And so what you want to do normally, let me finish my thought here. So zeta prime as a function of x prime is equal to zeta. Now let me replace this x with x prime. And so I should move this factor over to the other side. And I expand in small lambda, it becomes 1 plus lambda x prime. I hope you see that. Yes? And then there's this plus lambda. Make sense? I'm just replacing this x with e to the lambda. This means x is e to the lambda x prime, which is roughly 1 plus lambda x prime. That's all I'm doing. I'm replacing this x with this expression. And now, with the understanding lambda is small, then you Taylor expand. Yeah? Once you Taylor expand, you recognize what is the correct transformation. So zeta prime, x prime is equal to zeta at x prime plus lambda x prime. This is respect to x prime, of course, and then you do zeta. And then you add lambda to it. Does that make sense? Now I succeeded in writing the new field configuration as a function of x prime and the old field configuration at the same x prime. Now I can do the difference. The difference between them is what we call the active transformation on zeta. This is equal to zeta prime minus zeta is equal to lambda x. And you notice when I write this, I'm not being careful about whether I'm talking about x or x prime. I don't need to be, because these are already order lambda. So any difference between x and x prime here would enter at lambda square, so I'm going to just ignore it. So from now on, this is what we are going to do. So this is the transformation that supposedly should be a symmetry of your action. So symmetry of your action. Yeah. And it is really a residual gauge transformation. Remember, we went through yesterday, we fixed unitary gauge, we choose the spatial diff to make the spatial metric nice and simple. It's pure trace. other than gravitational waves. It looked like we have used up all the gauge degree of freedom, but it turns out actually not quite. There are these residual diffs that you can do. For example, this one. You are allowed to do it, and it's a kind of a diff transformation that is we call large gauge transformation. Yeah. So, for example, your gauge field shifted by an amount that does not vanish at infinity. Yeah. And infinity is stay constant. It's just a constant. So this originate. This is from large gauge transformation. Allowed after we fix all the small diffs. And when I say small, again, diffs that actually vanish at infinity, as opposed to these large ones. This diff actually, in fact, blows up at infinity. It grows with x. Okay? Questions about that? Yeah. Yeah, okay, good. So when I say large, I do not mean lambda is large. What I mean is the fact that this, for example, let's look at the gauge field. This is the gauge field. This is the metric. The amount by which it changed does not go to zero at infinity. When we say large, we are referring to its behavior at infinity. That's what we meant. It's a little bit of a confusing term. Probably there's a better term, but that's a very common term. This large gauge transformation does not mean lambda is large. It just means it's something that does not go away at infinity. Yeah. Any other questions? Well, knowing that this has to be a symmetry, you can imagine it's very useful. Because why? Remember yesterday we wrote down the quadratic part of the action, right? The action. Yesterday we wrote down the action is something that is quadratic in zeta. It's zeta square. We did not write down further, but you could have write down zeta cubed, zeta to the fourth, and so on. So the action, if you work hard enough, you should find all these terms. They are all there. The fact that you are sure this symmetry exists because you start from the very beginning a theory that has gauge invariance. So this must be a symmetry. And therefore, in this action, some of the terms here are fixed basically by this symmetry. What this symmetry does, because let's look at the structure. It has a part that is linear in the field, and it has a part that is independent of the field. Imagine you put this change into this action. Just imagine that in your head, how you do that, yeah? So if you change basically this one, there would be a part of the change that's linear in the field, and so after doing the change, it's still zeta square, yeah? But now imagine you apply the gauge transformation to this part. This part would have a term, one of the term where one of the zeta changed by a nonlinear amount, so it's independent of zeta. And so there would be a term in that change that is actually also give you a quadratic part. And it better be true, those two changes cancel for this to be a good symmetry. And so this kind of symmetry relates a second order term to the third order to fourth order, and so on. You see what I mean? And so this is very useful without even having to write down what they are, because you know it has to be there. Okay? And by the way, this we call dilation, because this obviously, I'm just rescaling the spatial coordinates, so we call this dilation. So this is the dilation symmetry. And it's just a purely spatial dilation. Okay? And from time to time, I would break this up into two parts. I would call this part the nonlinear part, of the zeta transformation. Sorry, the linear part, linear. And when I say linear, again, all I mean is this transformation is proportional to the field itself. That's linear. And this part is nonlinear. Okay? Nonlinear actually, maybe better term is actually sublinear. When I say nonlinear, I do mean it's zeta square. What I mean is it doesn't depend on, it's not linear in zeta. That's what I mean by nonlinear. Okay? So there's these two parts of the transformation. Any questions about that? And what we want to do today is to ask ourselves, well, knowing that this is true, what does that imply about the correlation function, including any endpoint function that you want to write down, 3-point function, 4-point function. What can we say about them? And you might remember already from yesterday, the puzzle I told you about shifting the gravitational potential by a constant. Somehow that example tells you the correct statement cannot be that the correlation function is invariant. That cannot be true. So what is the correct statement? That's what we want to derive, and those goes by the name of soft theorems. Okay. But to get there, I need to say one thing before we get there, and this is an important point, and I need to talk about the idea of adiabatic modes. So let's talk about that. It's important for the following reason before I even say what it is. Well, this symmetry, it looks nice, but it really comes from a gauge symmetry, yeah? And a gauge symmetry, as you know, really is no symmetry at all. It's just a redundancy, right? You are using multiple field configuration to describe the same physics, like multiple different choices of your vector potential that describe the same electric field, right? And so in some sense, gauge symmetry is just a confusing language. We are just confusing ourselves by introducing so many redundant variables, and so it looks like you have some kind of symmetry. But at the end of the day, you know, somehow your observations, your observable should not care about gauge anyway. And so, yes, you have this nice looking symmetry, but how can there be any physical consequence from it? Yeah? And it turns out, interestingly, in cosmology, there's one context in which you actually get a physical consequence, meaning observable consequence, out of what looks like gauge redundancy. And the idea have to do with adiabatic modes, okay? So I need to explain that to you. And this was nicely explained in a paper by Weinberg, Steven Weinberg. If you search Google Weinberg adiabatic modes, you will find the paper, okay? And so let me explain that to you. Let me try to explain it in 2 steps. So this is the first observation. It's almost kind of like a trivial sounding observation, but it's very useful. Let's think of this symmetry as kind of a device for coming up with solutions to your equation of motion. Let's say I just want to solve the classical equation of motion for zeta. And I hope you all agree zeta equals 0 is obviously a solution of the classical equation of motion. It's a solution. It's obviously a solution to the zeta equation of motion, whatever it is. If you are strong enough to write down all the nonlinear terms, it will be complicated looking. But for sure, zeta equals 0, which is just a homogeneous universe anyway. You know a homogeneous universe is a good solution. So zeta equals 0 is obviously a solution. Yeah? But once you buy that, then you say the following to yourself. You say, well, now let me do a gauge transformation on that solution. You see what I mean? But because I have a gauge symmetry, the resulting gauge transformation must also be a solution. You got that? And so if you start with zeta equals 0, you plug into here. This is 0, so you can forget about it. So all this does is to generate this constant. And so delta nonlinear zeta equals lambda. must also be a solution. It's kind of a trivial sounding point, but it's important that you can think of this gauge transformation as just parametrically, I just want to generate solutions from simple solution that I know exists. For example, zeta equals 0, you can start there, and then you can generate a solution. Yeah? So far okay. Now, one thing you observe about this procedure, though, is the following. If you think about everything I told you, there's nothing that demands lambda to be actually a constant in the sense of a constant as a function of time. Lambda could be time dependent. Yeah? Everything I did not make any assumption about what is the time derivative on lambda. And so this is my second point. So far, lambda can have any time dependence. Yeah? So far, it's actually, even though I did not write explicitly, it's really lambda as a function of time. And that function of time can be arbitrary. Yeah? And indeed, that's correct. So you can just check. If you put in this lambda as a function of time and just put in the zeta equation motion, it is a solution. And for any function of time. However, and this is what we call the adiabatic mode condition, we want to choose the correct function of time so that this mode, let's think about what this mode is. This mode, it can be a function of time, but it's independent of space. So it's obviously what we call a soft mode. It's a mode with 0k. Yeah? So this mode is a soft mode, very long wavelength mode. Yeah, you have generated a solution that has super long wavelength. In fact, it's just a constant in space, and so it's zero momentum. But in principle, it could be some function of time. But now we demand one thing that is actually physical. We say this mode that's generated by gauge transformation must have a time dependence that's a smooth limit of physical perturbation at finite k, and then taking the low k limit to 0. You understand? That's the adiabatic mode condition. So the adiabatic mode condition, so this is the adiabatic mode condition. Choose lambda t such that its time dependence agrees with physical, and I want to emphasize physical modes at finite k. So k is actually start with something that is actually not super long wavelength, that has a finite k, and then take the limit. This k go to softer and softer and softer, just stretch it. And when you take the soft limit, you want this time dependence to agree with the time dependence of physical modes. Does it make sense, everybody? And it turns out in cosmology, because you do that, now we actually can deduce physical statements that have to do with these symmetries, which originate from gauge symmetries. Let me pause here in case you have questions. Yes, please. Yeah. I'm not doing a time diff. I'm doing a purely space diff. So if I want to be extremely precise, I'm doing this, but I'm leaving time alone. Yeah. I'm not doing a time diff. I'm doing a purely space diff. And you can check. Just do the usual. I hope you know that from GR how to transform the metric under any diff. Yeah. And you can check everything I said is correct, even if lambda is time dependent. As long as you don't change your time coordinate, you are only changing spatial coordinate. Yeah. 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 From the point of view of just writing down something that solves the equations, you are free to choose any time dependence you want for lambda, because again, the idea here is this is just pure gauge, and you know your theory is gauge invariant, so you can just generate these solutions. But I want to make something more, I want to place an additional demand. I want to say this gauge generated mode, which is at zero momentum because it's independent of space, must have the time dependence that actually is smoothly connected to a physical mode. So let's draw a little picture now. So this is my physical mode. Physical mode at finite k. So its k is not equal to 0. It has a finite wavelength. And if I solve the equation of motions for this mode, it's going to have some time dependence if I'm strong enough to solve it. But now I'm going to imagine such a physical mode, and imagine its wavelength becomes longer and longer and longer. So I'm going to take this limit. So this is the soft limit. And in that limit, solving the equation for the physical mode, it's going to approach some kind of time dependence. I don't know what, but it will be some time dependence. And I just want to demand whatever lambda I choose here, match that time dependence. And therefore, I can safely say this gauge generated mode is smoothly connected to physical modes. You understand what I'm saying? They are not smoothly connected. And the reason why we insist, you will see in a moment, is we will be interested in correlation function. This is a little bit of a preview, right? We are going to be interested in correlation function that actually involve a soft k, this k going to 0. And then other things. We'll be making statements of that sort. And my point is the following. K equals 0 actually is not something that we can observe anyway. Infinite wavelength, right? We cannot actually observe that. But we can observe finite k things. What we can observe finite k things that are actually very long wavelength, much larger than, let's say, even larger than the Hubble radius at some point in the history of the universe. And in that case, the statement we're going to derive using gauge symmetry turns out to be correct. It will be because this, even though k is not strictly 0, but it is very, very small, and we'll define what very, very small means in a moment. But as long as that's true, the statement we derive using these gauge symmetry would apply to this physical observable in the limit when this is very, very small, basically. It's smoothly connected. That's the point of this adiabatic mode condition. Any questions about this? Any questions? It's an important point. It's a kind of a simple point, but it's something that you should always come back to and keep in mind. Yeah.
You have this huge definition, and then you want our goal is really lambda, you want to connect it to physical modes, so you find it to be the limits and so it's like gauge physics. You are posing something that
Yeah, I mean, at the level of gauge transformation, once again, you are allowed to do any. And this already obeys all the gauge fixing conditions that we usually impose, like the unitary gauge, like the absence of off-diagonal components in the spatial metric. So those Those are what we usually call gauge fixing condition. Here, it is true we are demanding that this gauge parameter, so to speak, also have some extra condition, which is the ideal condition. So you could call it gauge fixing condition, although we usually do not call it that way. Usually the gauge fixing condition that we impose are the ones that fix the small, basically the small gauge transformation, the one that vanish at infinity. Yeah.
The fact that here we are and normally analysis reminds symmetries large information, so I said the mode doesn't like gauge information doesn't vanish at infinity.
Uh-huh.
By building something at k equals 0, so it could be large to large scale distance.
Yes. Yeah. So the precise connection, once again, is this gauge generator mode, strictly speaking, is k equals 0. We want to make sure it's smoothly connected to physical modes that have finite k, but when you take the long wavelength limit, they actually match. That's what we want to impose. Yes. Yes, that's what a k equals 0 mode means. No, k equals 0 mode either is just 0 or is a constant in the sense of independent of space. Yeah. Okay. Any questions? Any questions? Okay. Once we do that, now we are going to use this. This is why I actually wrote this down. We are going to fix lambda now, because what is the time dependence for lambda? You might ask, right? Remember this equation. So this, I claim, if you work out the 0, 0, and 0i Einstein equations, one equation that you will get is from here. Okay? And we are now going to apply this reasoning to basically what is going on there. So again, remember point number 1. I can always generate solutions by doing a gauge transformation, right? So I'm going to start from 0, so zeta equals 0, and delta G00 equals 0, so it's a homogeneous universe. I'm now going to do a gauge transformation to generate solution. And so I can consider basically this one. I can generate this solution. I can generate this solution. I can generate both using nonlinear transformation. You can convince yourself, because our diff doesn't involve time, there's no time coordinate remains unchanged. In fact, this part is just 0 because we are not doing time diff. Even though lambda is a function of time in principle, this part is just 0. Whereas this, we just work out is actually lambda dot because there's a dot here. That's what this is. Yeah? You understand what I'm doing? Yeah? So I'm just rewriting this part. This part is from here. Yeah? Well, how about the spatial gradient? Well, the spatial gradient, if I do it in Fourier space, is some k square multiplying this. So apparently, based on this equation of motion, if I apply the logic of point number 1 of generating solutions, I'm going to now have this equation of motion. Yeah? Now, you want to demand that lambda is smoothly connected to physical modes, right? Which means you want to solve this equation in a non-trivial way. What do I mean by that? You want to solve this equation pretending k is actually not 0. You understand what I'm saying? And so the only way to satisfy that is to demand lambda dot is 0. So if you solve this equation with general k square, not necessarily a 0k, then this tells you that lambda dot has to be 0, so it's time independent. So this lambda turns out the only thing that you need to, this time dependent is really lambda is really truly both space and time independent. That's what we are going to focus on. This is the adiabatic mode condition for the dilation symmetry. For other symmetries, it will be less trivial sounding. You would have some non-trivial time dependence. But for dilation, it turns out to be very simple. You just do a dilation where lambda doesn't depend on time. Once you do that, you are guaranteed, let me just stress that again, you are guaranteed now, you are, by doing a gauge transformation, it's almost like a sleight of hand, you have generated something that actually is apparently physical. Physical in the sense that it's smoothly connected to finite k mode as you take the k go to 0 limit. And this is the important point, which is that when you solve this equation, you don't want to solve it trivially. Trivially in the sense that, oh, look, this mode is k equals 0 anyway, so it multiplies 0. So obviously this equation is satisfied. You could say that. That would be a correct statement. But we want to demand something stronger than that. We want to say, well, I want to solve this equation. If I am given any physical mode, a physical mode, at k not equal to 0, if you just solve this equation in Fourier space for any physical mode, you know this has to be true, no? You can just remove the k square. You know for a physical mode at finite k, you know this has to be true. And so we demand even our k equals 0 mode, the same is true. You understand what I'm saying? So we do not want to solve this equation in a trivial way just because you have a 0k mode, you are taking Laplacian of that, of course you get 0. We want to just remove this Laplacian, divide out k squared, and demand this is true, which you know this is true for physical finite k modes. Any questions? Yeah.
You didn't just start from integration, also from integration that goes to 0 in the k squared. Why you had to start from this case? Can you just find the solution?
You can find solutions. There are actually maybe two answers to your question. So the reason why we go through gauge transformation is, first of all, it's just a trick for getting solutions. We know that works. So if you are given the trivial solution, which is equal to 0, you can always generate a solution. So you know that works. And the reason why we want to use the gauge transformation, of course, is what I said earlier. This symmetry, actually, if you write down the action, they have zeta square, zeta cube, and so on. This symmetry is nice because it has a linear part and a nonlinear part, so it relates the quadratic to the cubic, cubic to quartic. And we are going to actually exploit that. That's what we're going to use. So we are doing more than just looking for solutions now. So that would be probably the answer to your question. Yeah. Are there other questions? Okay, so keep that in your mind now. So we are using gauge redundancy, but because of adiabatic mode conditions, we will be able to derive physical statements, physical consequence. Okay. All right. So what is the consequence? Well, to do that, I think I'm going to give you an exercise for today. Let's do some exercise. So let me define my convention. So my zeta, it turns out it's useful to go to Fourier space because we are talking about soft k going to 0 and so on. So let me just define my convention. So zeta k, I'm suppressing the time dependence. There could, in principle, be time dependence there. but I'm interested in the spatial dependence. And let's say I choose this sign. This is my definition of my Fourier transform. And my question to you is, we know this is true. The is equal to what I wrote down there is x dot grad zeta plus lambda, plus 1. I factor out the lambda there. So tell me, what is delta zeta on the Fourier modes? Do it now. Work out both terms. Yes, just doing Fourier transform. I'll give you a few minutes. Okay. Yeah, so do the Fourier transform with this. In other words, calculate this. Calculate this. This is equal to d3x delta zeta x e to the I kx now. Yeah, so figure that out. This part is easy. I hope you can all do it right away. This part requires some integration by part. So freely integrate by part, drop boundary terms, assuming zeta go to 0 far away. And I'm going to catch up on my breakfast while you're working. But if you have a question, just put up your hand. I'll come to you. So if you do it, I hope you agree. This part is easy. You're just integrating a constant, do the Fourier transform a constant, so it must be, let me pull out the overall lambda. This part must be just a delta function. It's a three-dimensional delta function at localized at k equals 0. I hope you all agree. And then this part, if you just do the integration by part and so on, roughly speaking, this x becomes 1 over k. And so this becomes a gradient respect to k. And this gradient becomes a k. So this becomes a k. Zeta k. You understand what I'm writing? That's it. That's the transformation. Okay? Any questions about that? And I think I might be missing a sign. Does anybody get a negative sign? Is it minus? Okay, good. I think that should be a negative sign, okay? When you integrate by part and so on, just be careful. I think there is a minus sign. Check that for yourself. So this is going to be the transformation we will use now. Yeah, any questions? Okay, so now we are going to do a little bit of a formal derivation, and we are going to use the wave functional at some point. So we are going to deduce a soft theorem, and it would be something like this. First, let's consider something. Consider some observable, and I'm going to call it O. For example, an example would be this observable would be, let's say, zeta at K1 and zeta at K2. I will be lazy and start dropping arrows on top, but these are vectors. Yeah. So, for example, this observable could be a product of 2 zeta, but you will see at the end, it turns out this theorem is so general, it doesn't really matter what that observable is. But to be concrete, keep this in mind. This is what a pair of zeta. And I'm interested in this correlation function, let's say. Yeah? Okay? In the language of wave functional, what would you say? You would say, well, this is a measure integrated over many field configurations of zeta of the observable, which you think of as a function of zeta. It depends on zeta in some way, times the wave functional for zeta square, right? That's what you would usually do. You do that in quantum mechanics. Yes? In quantum mechanics, you would be, this is an observable which is a function of x, let's say, or the derivatives. You integrate over x, the observable, you do the wave function square. That would be the normal thing you would do. I hope you all agree. Yes? And now I'm going to do something a little bit strange. I'm going to say, in the context of this writing, this zeta is a dummy variable integration, yeah? For which I can do any change I want. For example, I can, instead of calling this zeta, I can do zeta plus delta zeta. This delta zeta eventually is going to be that delta, or this delta. This observable. So let me be actually more explicit. So let's say this observable is a function of zeta, and so now This is a function of zeta plus delta zeta. And likewise for the wave functional, I should just replace zeta with zeta plus delta zeta everywhere. This I'm allowed to do because I'm not even using symmetry. This step doesn't involve symmetry. This step is just changing dummy variable of integration. So far what I've done have no physical content. It's really just changing variable of integration. So far so good. Okay, now the first assumption that I'm going to start making is that, well, let me just assume the measure, at least for this particular change, the measure remains unchanged. Which if you are familiar with what we do in path integrals, the fact that this holds is actually not guaranteed. And in fact, if you have anomalies, then you have to be careful. But we are going to go ahead and do this. Okay? I'm going to say this. You can just ignore the Jacobian. Usually there's a Jacobian. The Jacobian is infinite. But as long as it's not field dependent, you can just shove into the measure. So that's what we're going to do now. You okay with that? And now I'm going to say this is equal to that. So let me subtract them. I should get 0. Yeah? And now I'm going to assume this delta zeta is small. This is small. After I do the subtraction and I should get 0, now let me write out the first order term. The first order term better sum to 0. That's the idea. You got that? So the fact that this is 0, the fact that this is equal, the fact that they are equal means you can subtract one from another, subtract one from another. Read off the linear contribution in delta zeta, assuming this is small, and those terms better sum to 0. That's the trick, okay? Yes? So far, I'm not using symmetry yet. This delta zeta in principle can be anything. Yeah.
If you, in principle, give us every single order, and then you get
you won't actually get new things. You won't get new statements, it turns out. Yes. Yeah. Actually, maybe I should hold that thought for a second. Actually, you will learn new things, and the new things have to do with basically not the soft theorem I'm going to show you, have to do with the double soft theorems. So you have not one Goldstone mode, but two Goldstone modes. Yes, you're right. Good question. Okay, any questions about that? So far, no symmetry use. It's just a trick. Now what I want to do, I think I want to use this board. So let's collect the first order terms now. So 0 must be equal to the first order terms. And what are they? Well, we can just read off. Imagine you move one to the other side and you subtract. Let's see if you agree these are the first order terms. First of all, there's a term that has to do with the fact that the observable is computed at the shifted zeta minus the observable at the or at the original zeta. So I'm just going to call that delta observable. So when I say delta observable, this is really the observable at zeta plus delta zeta minus observable at zeta. This term, there will be a first order contribution, assuming delta zeta is small. And then for this part, I can just keep it at 0 order. So there will be this term. Yeah? So if you look at that expression, there would be a first order term coming from variation of the observable. But there will be one more, and that's important, one more first order term that comes from variation of the wave functional. Yeah? And so that would take this form. This is the observable. And I will just write it this way for now. Delta psi star, plus complex conjugate. And what is delta psi? Delta psi is psi at zeta plus delta zeta minus psi at zeta. Okay, just schematically writing this way. I hope you agree. Those are the first order terms. So either the first order comes from the observable or the wave functional. That's it. So they must cancel to give you 0 because you are subtracting two things that are the same. Once again, so far I'm not even using any symmetry. Any questions? Yeah. Say that again. In the what? Yeah, that's what I assume. I assume the measure is unchanged. That is an assumption. And you have actually seen something like that before. In field theory, very often when the measure actually is changed, especially if it's changed by a field-dependent amount, that's when you have anomalies. So I'm assuming you don't have anomalies here. Yes. However, if you are trying to be super careful, when you change the when you do this kind of change, the measure actually does change by some amount that's field independent, and you have to be a little bit more careful. But usually we are not too careful about the normalization of the measure, so I just absorb it all in here. But you can try to be more careful about that. Yes. Okay. Any questions? Or you can just explicitly check. You say, well, I can just check my delta zeta. Does it change the measure in the way that is non-trivial? And you can check it's fine. Any questions so far? Okay, now I'm going to do the following. I'm now going to say, let's look at these two parts individually. Let's look at this part. Like this delta observable. Somehow, so far, it's so abstract that it's good to be a little bit more concrete. So let's say the observable is indeed 2 zeta multiplied together. So let's consider this example. Zeta k1, zeta k. Let's consider this. Yeah. Well, then this has to be basically this k1, k2 plus zeta k1 delta k2. Yeah. And now I'm really going to use this understanding now. This is your transformation that we are interested in. So let's put delta zeta to be basically this. Okay? And let's look at the two contributions. This is coming from delta linear zeta. This is coming from delta nonlinear zeta. Yeah? Let's look at the nonlinear part. The nonlinear part, in other words, this has two parts, delta linear plus delta nonlinear. Let's look at the nonlinear part first. The nonlinear part doesn't depend on zeta, right? And so this thing now, if you look at this part multiplied by this zeta, this product is just 1 power of zeta. Yeah? And if you evaluate this thing like this, you end up evaluating a 1-point function. You agree? This part multiplying here has just 1 power of zeta. If you plug into here, you are just computing a one-point function, which we usually say is 0. Yeah, you just set the one-point function to 0. And so at least for this example, it turns out you can just completely ignore this and just only keep this. Because one-point function for zeta is 0. Any questions about that? Should I repeat the argument? You got that part? Let me repeat again. No? The nonlinear part, which is basically just this delta function, is independent of zeta. Once you multiply this, that product has only 1 power of zeta. We are supposed to evaluate this under basically this path integral, evaluating using this wave functional square. So we are basically computing the one-point function of this object, which basically usually we say, well, the one-point function is 0. Yeah. Zeta fluctuate, but it fluctuates around 0, so the one-point function is 0. Yeah? And so the only thing that you need to keep is, in fact, this part. And so, and this part, we have already worked out. You nicely work out over here. And so you have basically, there's always a factor of lambda, but you have basically minus k1 dot k1 zeta k1. You have basically this part multiplying zeta k2. This is the structure you're going to get now. This change in the observable is going to lambda times this. This is the linear transformation on k1, zeta k1, times zeta k2, which is unchanged. And then you just add this term. And adding this term is just exchanging 1 and 2. So I won't bother writing down again. But that's it, no? And so I am going to write this way. Let's see if you agree. Yeah, I'm going to use this. So of these two terms, let me just say, let me give them names now. So that's term number 1, and that's term number 2, these two terms. Term number 1 turns out to be equal to, let's see if you agree with me, is lambda, there's always an overall lambda, minus grad k1 dot k1 plus k2 dot k2 acting on zeta k1, zeta k2. You understand what I'm writing? Let's see if you buy it. Yes. Yeah, lambda is just a constant, so you just multiply. So I should just say this lambda. Not lambda minus, but lambda multiplying. Thanks for asking, yes. In fact, lambda is going to just cancel out from both 1 and 2, so at some level, I don't even need to keep track of lambda. Okay? Yes? Excellent question for that mode. So we should now think about basically the quantum mechanical aspect. No? So we say, what does quantum mechanics tells you? It tells you that there's some wave function that tells you things fluctuate, and it fluctuates on all scale, including the very, very long wave scale. And so even though we say it's a constant, there would be some realization in which that constant is over here. There will be some realization in which the constant is over here, right? So it's a whole ensemble of possible realizations. You should think of it that way, right? Does that make sense? Any questions about this? I'm skipping some steps, but I hope it's kind of it's not too bad. Meaning, just think of one like this. When I write something like this, of course, this is the same as just writing this. No, that's what this is. Yeah, I'm integrating this, whatever this object is, over the wave function square, which is the same thing as computing expectation value for that object. And that's what I'm doing here. And then I basically say, well, we can compute delta observable this way. And then once you combine those two terms together, you will just get this. Yeah? So that's term number one. Let's think about what term number one means. Term number one basically means the following. You have a two-point function, and you ask yourself, how does this two-point function transform under basically dilating, changing the scale of k, which is what this operator effect. And the key point I want to say is the following. There is term number two there, and it's non-zero. And so we do not say that your two-point function is in fact dilation invariant. If it were dilation invariant, you would just set this to 0. But there is term number two. Term number two tells you, no, your two-point function is not dilation invariant, in fact. There's going to be a soft mode involved in number two, as we will see. Okay, so now let's look at two now. Any questions? Okay, so now let's look at number two. Number two, it sounds, for number two, we have to think a little bit harder about what is the change to the wave function now. The wave function now is the wave function now as a function of zeta plus delta zeta minus, is supposed to be this, no? Okay. Now I'm going to do something that is a little bit quick. If you think a little bit hard about it, it doesn't sound very legal actually, or very kosher. You should not do it, but I'm going to do it anyway, and now I'll explain why I can do it. But the why actually turns out to be quite important. So, but I'm going to go ahead and do it anyway. So I'm going to say, well, look, we have this nice wave functional. Let's just use it. I'm going to say that wave functional over there is this wave functional. Let's just ask, if I change zeta in the particular way that I described over there, how does the wave functional change? You see what I mean? Let's just go ahead and calculate. You are going to have questions, I'm sure, on why we are allowed to just use that wave functional, this wave functional here. Let's postpone that for a moment. I'll just calculate, and then we'll come back to why we can do this. Okay? So let's go ahead and just do it. So this wave functional is an exponential. In the exponent, there are 2 powers of zeta. Yeah? And then basically I ask myself, how does this change? And I'm only keeping track of first order terms. And the first order terms would be, because it's an exponential, you can imagine the first order terms would be proportional to the wave functional itself. I'm just doing something very simple. If you ask what is the variation of e to the minus x squared, I hope you will all agree, is e to the minus x squared times 2 delta x with a minus sign probably. No? You agree? Yes? The variation of this, you would say, is this. I'm doing the same thing here. Yeah? So I'm going to write down the wave functional again, and then now I have these things now. Minus, and crucially, sorry about that, there's a half here actually. So that I forgot to put down. So there's this, there's a k over 2 pi cube. There's 1 over 2 p zeta, k, plus an imaginary part that you will see in a moment, it would disappear. So I'm not going to care about that. And then I have basically delta zeta k, delta k star, both of them. Okay? Do you agree? Sorry, not both of them. The delta k, I'm only changing one of them. And all I'm writing there is just a more complicated version of what I'm doing here. That's all I'm doing. And in fact, sorry, I already messed up now, did I not? This is equal to, yes, I already messed up. So this is equal to this. There is a delta x and there's an x because I'm varying x squared. Yeah, there's an x, there's a delta x. And that's why I have a zeta and I have a delta zeta. I can, in principle, vary the complex conjugate also, but you will see in the end, those two terms combine in the same way and cancel the factor of 1/2. So that's why I eliminate that 1/2 and just do this. Any questions so far? Again, it's just a more complicated version of doing this. Yeah. So if I want to be super careful, really, I should do this. I should keep the 1/2, and then I should do plus k delta k star. That would be the more careful thing to do. That would be correct. So because you have 2 powers of zeta here, you can change one or the other, right? Yeah. But you will see in a moment the terms that we care about, they turn out to give us equal things, and they will cancel this factor of 2. Oh, yeah, this is a good question. So this is just the change to the wave functional itself. So it's basically just this. There's of course a complex conjugate of this whole thing, which is basically delta psi star psi. There's that too. So I'm just focusing on this for now. You agree? Okay, now we are going to do the following. Let's just study what is going on here. This one again has a linear and nonlinear part, right? Remember this one? There's a linear and a nonlinear part. Yes. The nonlinear part is going to give us the soft zeta. So the nonlinear part over there, the nonlinear transformation is a delta function localized at k equals 0. Yeah? And so if you put that in here, imagine in your head, you put this part, put it into here. This is just a delta function at k equals 0. You integrate over k. You are now setting this mode to k equals 0. This is going to be our soft mode. You understand? And structurally, I hope you can see, I have a soft mode multiplying the following. So from 2, the structure of 2, what is like the structure of 2 is look like? It looks like this, no? Like this. I have my observable, let me be precise, my observable is zeta k1, zeta k2, let's say. And then I have this change, but let me focus on 0 into this basically nonlinear part, which is a delta function that set this to be k equals 0. You agree? And so it looks like I'm going to have a soft mode, k equals 0 mode. It looks like from that kind of contribution, I'm going to get something like this. Now this side, we combine with that side star, we just give you psi square again. Do you see what I'm trying to say? Now, of course, I'm not being careful because there are these other terms I should keep track of. So there are other things around. What are the other things around? Let's actually be more careful. So the 2 pi cube goes away because there's 2 pi cube here in the delta function. There is this power spectrum. So I do have this power spectrum. And it is 2p zeta of k. Yes. Plus the imaginary part. My claim is you have to do that, go through that, the math yourself. This imaginary part is going to get canceled if you look at this term. These two terms would combine, eventually cancel. I hope you can kind of see that it's plausible. Yes. Sorry? Yes, because look at this integral. This integral, this is a delta function of k equals 0, so both of these must be set to 0. So this is also k equals 0. Thanks for asking. Yeah? So with my claim, there are these two terms. They are going to be the same. That cancel this 2, so the 2 is gone. There's 1 over 2p here. But then there are these two terms, this one and this one. They add in the real part to cancel this factor of 2, so that's gone. And so my claim would be, if you follow my procedure, this is it. This is going to be the following. This is the 3-point function of k1, k2. Let me just call it k, with k in mind to be sent to 0, divided by the power spectrum of zeta at k going to 0. That's actually term number 2. But I have a lot of comments to make about reaching this result now. But let's see if you are with me. There is, of course, lambda. The nonlinear transformation multiply lambda. So there is lambda here. This multiply lambda. And so this whole thing, there is really a lambda if you want to keep track of lambda. And therefore, there is a lambda here. But otherwise, I think I'm not skipping anything. But let me pause for questions before I make several comments. There are actually many comments to make about this. Yeah. Yes. Yeah. Yeah. Uh-huh. Yes. I see. Good. You should think about it this way. In our computation, setting these two terms and adding them to 0, what are we actually changing? We are changing the field. We are changing this field. This is the field that you have to change. Anything else is just a given function to you, a given number to you. You don't change them, including this one. Whatever that is, we are not changing that. It's just some known function of k that's given to you. What you are changing is actually the field in your path integral, and so you change this. That's what we are doing. Make sense? Somebody tell you what function of k it is, then you just use it, right? And then you say, I'm just going to vary my field. Is there another question? Yeah. Sorry? Good, good. That's one of the comments. Thanks for asking. So then you ask, how about this part? So this part, I'm going to use the sleight of hand now. So this part is proportional to zeta. This part is also, this proportional to zeta, this also proportional to zeta. So there are 2 powers of zeta here together. And you are supposed to integrate over all momenta. Yeah. It turns out you can show when you do this and you integrate over momenta, you are supposed to think of this wave function after all. Think about this wave function. This is really the wave functional in the far past. If you think about it, it's really zeta in the vacuum in the far past. And it turns out if you think carefully about it, these are going to be, this multiplying that are going to be rapidly oscillating things. And once you integrate over all momenta, they are just going to go away. So it's the analog of what eventually in scattering that we would say, oh, these nonlinear terms, they actually, in the far past, they actually do not generate single part. You are basically, you're going, they are not going to matter. You are going to basically focus only on the single particle states, basically. I'm not explaining this very well. Let me try again. So, and here is the subtlety, and it's related to the question that you're asking. Let me try to explain again. So, clearly, I'm actually being a bit sloppy about the use of this wave functional. So, let me do it here. And so far, I'm actually not super careful about time. So let me now actually put in what time we are interested in. So remember, we started off being interested in this correlation function, right? Now, usually we are interested in observable at late times. Remember this picture that I drew yesterday? So this is the Hubble radius. And these are how the wave mode gets stretched as a function of A. This is A. This is A over K. Remember this, right? We are usually interested in what is the fluctuation spectrum like at the end of inflation, this end of inflation. We are interested in, okay, what is the power or the correlation function at this scale at the end of inflation? So at late times, basically. So we are usually interested in this at, let me call it T final at late times. And so if I'm careful, when I do this path integral, this really should be the wave functional of zeta at the final time. That's what I meant. Okay? And the wave functional of the fluctuation at the final time is not going to be this. For one thing, we have an interacting theory, yes? In an interacting theory, clearly, the wave functional cannot be a Gaussian. There would be cubic terms and so on, yeah? So the wave functional is actually not this, despite the fact that I do my derivation pretending it is, okay? So that's comment number one. So what do? We are interested in, we want to know how this actually changed. And this is what you do. You say, well, now you are going to really do a path integral in the following sense. So I'm going to integrate zeta, let me call it zeta tilde maybe. And I'm going to say this is equal to, let me remind you what this is now. This is zeta at T final, taking the norm, the dot product with the vacuum, yeah? That's what this is. And so I can do this by inserting Tf zeta Ti zeta Ti 0. Yeah? And let me do this. Let me do this. Okay, so all I have done is I insert a complete set of states in between these two. I call them zeta tilde at the initial time, so in the far past. You are following me? So these are Heisenberg eigenstates. They are a function of time. So this part is the usual path integral that you are familiar with. Usually you do a path integral. You say, oh, I integrate. In fact, let me use slightly better notation. Sorry about that. So instead of calling it tilde, let me call it initial. So I'm going to call it this way. So the integration variable, I'm going to say the I. Okay. And you have to do a path integral to compute this amplitude, which is the field configuration going from zeta I to zeta. So you do, let me call this as zeta tilde, with the boundary condition that you go from theta I to zeta. This path integral would give you this dot product. You agree? So once again, let me just say this again. I'm interested in observable usually at late times, at this time, at the end of inflation, say. I'm calling that TF. To calculate the expectation value, I should use the wave functional of zeta at that time. You have an interacting theory. We have no right to use a Gaussian wave functional for this wave function. And so let's think about what this wave function is. This wave function is basically this, which is, you can think of it as the initial wave functional evolved using basically the propagator or the path integral to the final field configuration. That's what this is, right? You agree? And the point is the following. Suppose I now want to ask, under symmetry, under my delta zeta, how does this change? Then that's what you would do. You ask yourself, okay, how is this going to change? You do the following. TF 0. This is the change that you are trying to, you want to know what's the difference of this from that, right? That's what you're trying to do. And so you plug in, you say zeta plus delta zeta TF, zeta I, Ti, zeta I, Ti, vacuum. Yes. And now you pull the same trick as what I was doing before. This is a dummy variable integration, zeta I. So you're free to call it whatever you want. So I'm going to call it this now. Yeah? I'm just changing dummy variable integration, the same trick that I did before. Okay, so this is dummy change. And once again, I'm going to assume the measure has no subtlety. I will just say this is actually unchanged. This now, you can see, is actually directly related to now the initial wave functional, the wave functional in the far past. And as typical, as usual, what we do in quantum field theory, and you can make that more precise, this vacuum wave functional in the far past, when Ti go to -infinity, to very good approximation, you now treat it as the free wave functional. which is basically what we have up there. You might ask, how about this part? This part is where the physics is, it turns out. If delta zeta is truly a symmetry, then the physics tells you the evolution from this configuration to that configuration must be the same as if the transformation is not there. This is where the physical assumption of symmetry actually is hidden. The fact that delta zeta, if you look at my derivation so far, I did not really use the fact that delta zeta is actually a symmetry. It's just some transformation. But the crucial part is, because it's a symmetry, it respects basically this dynamics. The transition amplitude from some initial zeta to final zeta is the same as this transformation if you transform the initial configuration and the final configuration in the same way. Using that symmetry, this is preserved. So if you follow that logic, this is in the end why we are allowed to use the free wave functional. But it requires more work than we have time for to actually follow through and do the calculation. And what I can tell you is, if you follow through with one more technical assumption, you will arrive at the same result here. And if you are interested in the detail of this derivation, at least derived this way, you can look at this paper by me, Joyce, and Wong. You can find this derivation in that paper. And so let me just summarize, and then I'll let you take a break. So what I want to impress upon you is that at the end, the soft statement is actually very simple. So the soft statement is the following. The soft theorem. So dilation, soft theorem. By the way, in cosmology, these are often called consistency relations. And we just derive it. If you just match what I wrote about term number 1 and term number 2, they are both proportional lambda, so remove the lambda. And I'm going to move term number 1 to the other side. And so I hope you see I have basically k equal to 0, k1, k2, power spectrum of zeta k equal to 0 is equal to k1, k1, plus these are vectors, k2 dot k2, zeta k1, zeta k2. So this is the dilation consistency relation. And they are always of this form, that on the right-hand side, there is some observable. And then on the left-hand side is the same observable with the addition of a soft mode. Schematically, it's always like that. You got that? Any questions about this? It's a little bit of a longer derivation than I was planning on. Any questions? Let me make some comments about this now. So comments. I'm just going to write this here. Okay. So the comments I want to make is the following. Number one, if you follow this logic, the way this is derived, I'm using symmetry. I have not actually done perturbation theory. Yeah, which means these statements are actually good beyond perturbation theory. So these statements work beyond just the lowest order perturbation theory. You can include loops if you want. This should still be satisfied. Okay, so that's my point number one. Point number two is that if you follow my logic, in fact, it's not so crucial at the end of the day that the observable is these two zeta. It can be any observable. And so the second statement I want to make is this schematic form is in fact faithful, meaning, of course, there is this always divided by power spectrum of zeta at k equal to 0. That's probably a more accurate schematic form. But the second statement I want to make is the observable can be very general. You can give me any observable you want. There would be a statement of this sort. That would be correct. And I want to stress this is actually very useful because think about what we observe in cosmology. Very often, we measure correlation function not only in the early universe like in CMB, we measure correlation function of galaxies that forms in the later universe. And these observables can be just the galaxy counts themselves. You are asking, what is the density of galaxies over here versus over there? You can do correlation function of those galaxies. And the claim is, even for those, this will work. Yes? And galaxy formation is complicated and nonlinear. The claim is this statement will still work. Yeah? And so that's a very powerful statement that the observable can be very general. And in the case applied to galaxies in particular is very useful because this observable, in general, this K1, K2, for example, that I was using, in general, basically what you should do is you observe a 3-point function. You take one of the modes to be very soft, and here we can be more precise. Soft means what? Soft compared to these modes. And these modes can be actually arbitrarily hard. And in cosmology, you might know, when you go to small scale, high momentum, again, things are very nonlinear. The gravitational dynamics is nonlinear. It's very hard to get robust predictions. This is one of those robust predictions that you can count on. Even if this K1 and K2 and so on, Kn, is high momentum. So observable can be very general, and in the nonlinear regime. Okay, and number three, I think that's probably an important point, maybe the most important point. If this is so general, if this always works, what do we learn from it, actually? Do we learn anything? And it turns out you actually learn something. So I don't want to overstate the case. This is always true, but that's one caveat. There's actually a hidden assumption in all these. If you look at basically what I did here, I am assuming there's basically 1 degree of freedom that controls everything, basically zeta, yeah? Zeta is basically this soft Goldstone mode. It's basically like a Goldstone boson. We have a nonlinear realized symmetry, which is basically zeta. This is equals a constant. The fact that you have this means you can really just think of this as a Goldstone. You have a soft Goldstone that actually controls everything. That's why you are able to write down this kind of a soft theorem. Imagine you have a kind of inflation model which is more complicated. Imagine you have an inflation model where there's the inflaton, but there's also other fields around that also determine the perturbations. In that case, you can still write down some soft theorems if you want to, but those soft theorems had better include the transformation of these other fields. And therefore, checking in data whether this is true becomes a test of this single field assumption. So this observing or checking this in data means a test of single field slow roll inflation. If you have, it's not actually hard to come up with models where you can still write down soft theorems for them, but they would take a different form. There would be, you would have this, but you have additional things. So if you check data to see if the minimal form is correct, you are actually testing some very basic assumptions about whether in the simplest model of inflation, there's basically this single inflaton that is the clock that provides a clock for everything else. It's the single fluctuation that determines everything else. And provided that is true, then this form of the soft theorems holds, and you can check this with the data. And in that sense, it's a very physical thing, meaning if you violate these assumptions, you would get something else. And this is something that you can check with data. So that's maybe the last remark I would make. We are running out of time. Any questions? Any questions? We will tomorrow wrap up this discussion of soft theorems. There are actually more things to say about soft theorems and how they are useful in cosmology. And then we'll move on to talk about black hole perturbations. Okay? Thank you, everybody.